Thank you very much. So before I go talk about this, I just want to do a quick poll. How many of you have not heard about RISC-V? Oh, OK. We're doing pretty good here. So I changed the title. I was originally designed in the next billion chips, and I was like, heck, let's go for trillion. So today I'm going to talk a little bit about design economics of chips and how we got here and how we might change it. Our imagination is endless, limitless, and we keep coming up with these new workloads that need a lot of compute. Beforehand, when Moore's Law was going really great, there was really nothing you could do. Or software, you have written software, and you just wait for another 18 months, and another better processor comes out. Designing hardware takes about 18 months, too. So if you went and specialized your hardware to accelerate your thing, you'd be lapped by the new processor. So there was really kind of not a good reason to go build your custom hardware back then. But we all know that we've forgotten how to build chips with $1 million. A 16 nanometer chip is known to be at least $50 million and things like that. So I'm here to propose today, so how do we move forward? How do we attack this? There's endless computing needs, and there's no longer more transistors that are cheaper. So we got to do something about this. So I'm today going to propose that we copy the success from software. So I'm going to talk a little bit about that. So most of you probably know Instagram, right? Does everyone know that Instagram was sold at $1 billion when they were 13 engineers? That's like $80 million of value per engineer. Gosh, I was so jealous about the software industry. The day I read the article, I'm like, gosh, maybe I chose the wrong profession or something. Because have you heard about a $1 billion hardware company that was 13 engineers? I actually counted how many engineers you needed, and I counted 14 at least. You need somebody who knows architecture, microarchitecture, RTL, backend synthesis, timing analysis, packaging, fab relations, and all that. It's not great, right? So after really kind of collecting myself, after kind of being jealous and all that, I kind of thought about why that's the case. So this is the Instagram tech stack, what type of technologies they use to go build their applications. As a matter of fact, you go search internet here, techstacks.io, and everyone shares what type of technology they use. There's a lot of open source technology that was used to go build Instagram. And so it's ease of development. You don't need to build your entire foundation from scratch. You can go leverage a lot of stuff that was out there already. And couple that with ease of deployment of your application. The whole value proposition of sharing your photos and things like that is you have a lot of people to share it with. And in order to build that infrastructure by yourself, that's almost a monumental task. So rather than going and building your own compute infrastructure from scratch, what software folks do is they go rent servers from Amazon. So you can roll out your application quickly, and you can get quick feedback on how why your application is not being used. So you have a chance to go change your applications and things like that. So let's kind of think about a typical hardware startup's tech stack. Is there any open source technology? Is there any ease of deployment system? Well, that's why I'm here today, to talk a little bit about that. So we're making progress. I'm happy to report that we're making progress. So there's RISC-V. It's a free and open instruction set architecture. There's also NVDLA from Nvidia. It's an edge learning accelerator that recently was announced from Nvidia. So there are more companies who are jumping on the bandwagon of open source hardware. But think that you had all the RTL necessary to go build your chip. You still have to go build a chip. That's a lot of work. And the missing part over there is where I'm going to propose where SiFive fits in. So we're building a cloud service to go help build your next chip. So that's where SiFive fits in. So a brief introduction about RISC-V for the folks who haven't heard about RISC-V. RISC-V is a 5th generation RISC designed from Berkeley. Here are the 4 RISC projects that were done at Berkeley in the 1980s, RISC-1, RISC-2, RISC-3, and RISC-4. There were 3 chips for RISC-4. So we've designed RISC-V to be good for all computing platforms like microcontrollers all the way up to supercomputers. There are multiple open source and proprietary core implementations. And the different thing is that RISC-V, we encourage you to go build custom extensions by it. And there's a huge growing software ecosystem. Most of the software packages that you know have all been ported to RISC-V, and there's a lot of Linux operating system, FreeBSD, Zephyr type of operating system ports out there. And the standard is maintained by the nonprofit RISC-V Foundation. So as Rich told you, I started the RISC-V project when I was a graduate student. So if you kind of see the development timeline, it's not like, it's been about 8 years since we started the project. So we started the project in 2010. And what we did is we were developing the ISA alongside a bunch of different tape outs. And we would build compilers, we would build operating systems, we would go write RTL, and we would keep iterate on the RISC-V ISA. So after 5 years, we only started the RISC-V Foundation in August of 2015. And 1 month before that, we started SiFive. And at SiFive, we've been building a lot of core IP for RISC-V. We've been developing chips and development boards so that people can go and really build their RISC-V solutions. And recently, we've rolled out our first service to help people design core IP. And that's called the Core Designer, which I'll show you in a bit. So this is just an old photo when at Hot Chips we were doing the first RISC-V rollout. What's the best way to get noticed? You dress in the same T-shirt and you just walk around. So this was the initial RISC-V team. You can kind of see Dave Patterson on the most right, the bald guy there. And the tallest guy in the back is Chris Asanovich, my advisor. This was the initial team who went and built RISC-V. So, kind of the core values of RISC-V of being simple and, something that you can play around with was almost necessary because we only had a core team of 12 people, around 12 people to go build RISC-V. So now RISC-V has grown up quite a bit. There's more than 100+ member companies in the RISC-V Foundation. Samsung, thanks to Samsung is part of the RISC-V Foundation. So that's great. You can kind of see a lot of big giants in the industry being part of the RISC-V Foundation. I'd like to talk a little bit about the RISC-V industry adoption. Large companies, some of them actually went public about their status of adopting RISC-V. Nvidia has publicly announced that GPUs are going to use RISC-V as part of their microcontrollers. Western Digital publicly announced last year of their transition of a lot of cores to RISC-V. So currently, the industry adoption kind of starts from replacing a lot of homegrown and commercial cores to RISC-V. The RISC-V Summit, the next one, will be held at the Santa Clara Convention Center from December 3rd to 6th. So if you're interested, please come. There are keynotes from Western Digital, Microchip, Facebook, SiFive, NXP, and Qualcomm, and some other companies. So RISC-V has also been adopted by some governments. India has adopted RISC-V as their national ISA. So a lot of things are going to be mandated to use RISC-V. DARPA has mandated RISC-V in a lot of their upcoming security programs. And there's some other countries that have been embracing RISC-V for various things. This is one of the most exciting things about RISC-V to me, that RISC-V is now being taught at universities. I've been trying to convince Dave Patterson to go change his computer architecture book to RISC-V, and it happened 2 years ago. And Dave, being smart, he came to Andrew and I and said, hey, I'm considering changing the book to RISC-V. Are you interested in helping me out? So Andrew and I changed the previous edition that was in ARM to RISC-V. So now a lot of the undergraduate curriculums are teaching RISC-V in schools. So I think since it was 2 years ago, if we wait about a year, now you'll see actual undergrads coming out of schools with RISC-V knowledge. So the reason why I think that's really cool is because the thing that we teach in universities and the things that we use in industry are actually the same thing. It's not like you've learned this fake ISA in the book, and then once you go work at a company, the first thing is like, oh yeah, forget about everything you've learned. Here's the real thing, and 10 volumes of the book. Go read the real architecture. So we can remove all those inefficiencies now. So everyone's coming out of school. They've been taught RISC-V during undergrad, graduate curriculums. And the graduate book also has moved to RISC-V, and a lot of research is being done in RISC-V. So a lot of people will be up to speed on RISC-V. Also, one nice thing about RISC-V is since it's a free and open instruction set, a lot of people can freely communicate their ideas in code. If you have a good idea around a computer architecture, you can freely hand it out to other people and research and collaborate together. So by now, you're probably wondering, how good is the ISA? So OK, I understand it's all free and open. So how good is the ISA? It's kind of really hard to compare ISAs to each other, apples to apples. So I pulled some data here. So I'm going to show you static code size compiling a known benchmark, spec 2006, to RISC-V and a bunch of different ISAs. I'm also going to show you dynamic bytes that were fetched to go execute the program. So the one on your left is 32-bit architectures, and the one on your right is a 64-bit architecture. So everything is normalized against the compressed 32-bit RISC-V ISA. You can see that it's smaller than x86, comparable to ARM, Thumb 2, and way better than the MIPS architecture. So static code size matters for embedded systems where you have limited code storage. So having a smaller code base matters a lot. So 32-bit RISC-V looks pretty good. If you look at the 64-bit architectures, you can see RISC-V 64-bit ISA has compressed instructions, so it is doing really well. ARM v8, when they moved to 64-bit, to my surprise, they actually dropped the compressed instructions. So now RISC-V is doing really well in static code size. So that's pretty good. So having a smaller code size matters for high-performance systems too, because that means with the same instruction cache size, you can pull in more instructions into the same cache. So that's pretty good. So let's look at dynamic bytes fetched to do the same application. So if you can fetch less number of bytes to execute the same program, that means you're saving a lot of energy because you're moving less bits around to do the same program. So if you go look at the geomean on your right, you can see that RV64GC, the compressed version, is doing quite well compared to the other bars, including x86, 64 there. So I'm here to claim that RISC-V is a pretty decent ISA, which is free and open. That's all. So switching gears into the NVDLA part that I was talking about. So this is Jensen Huang, CEO of Nvidia at GTC, proudly announcing their open source efforts into the Edge Inference Accelerator. So the reason why I'm showing you this is because this is a movement, open source hardware, and I hope more companies would see the benefit of open sourcing certain parts of hardware so that a lot of other people can go benefit. And I believe, I haven't talked to Jensen about this, but I can only speculate why he did this. I think what he's doing is, if there's a lot of edge inference chips out there, there will be more training that is needed for those edge inference. And GPUs are used a lot for training, so this all makes sense in terms of business. Great. So I'm going to switch gears a little bit and show you a little bit about our cloud services that we're building. So this is SciFive Core Designer that we announced about a month ago. So the whole idea is that you can come to our website, use the web application to go customize your core IP. So there's a lot of the knobs that you can turn to go change your processor. And you hit review and you hit build. And after a couple hours, you would get a delivery for the core IP that you need. So this is one of the services that we're building to help you build your chips easier. And the 7 series cores is a dual issue in-order processor that we built. The S cores are the embedded version of it. The U cores are the Linux version of it. So what you can do with the Core Designer is you can mix and match these embedded and application cores. And all the cores that you can build are parameterized with ECC options, floating point options, bus complex configurations, the L2 cache configurations, the type of ports, the memory maps, and things like that are all configurable. So you can build a core just right for your application very easily without talking to a lot of people. So that's kind of the Core Designer. So I'm going to move to our second product. It's called the Chip Designer. So the idea is, in order to simplify chip design, what we have to do is we have to lower the cost of entry, where there's so many things you have to know about building chips. So our bet is that we would build some chip templates which are customizable, which have all the process technology nodes, the core IPs, a lot of peripheral IPs already all put together and configured, so that once you want to come and build chips, you can start from a template that has already been pre-integrated, and the process technology nodes have been considered. A lot of IPs from the ecosystem has been considered, and there's a reference chip that's been taped out. The reference chip is on a development board, and the board support packages have already been out. And with that, you can go and start working with the board and the chip, and you'll go figure out what types of, the chip has not been really customized for your needs. So you can kind of see that once you click a template on a web application on your browser, there will be all the IPs that were pre-integrated in the template in the middle. So this template has a gigabit Ethernet media access control block. There's PLLs, there's some peripherals, and there's a core complex in the middle. And on the left, there will be all the IPs that have been onboarded onto the platform on the left. So you can go change your SoC design, you can add IPs, you can remove IPs, and all that. So this entire infrastructure would be running on the cloud, Microsoft Azure or Amazon AWS, for example. And on the cloud infrastructure, there will be these EDA tools already onboarded onto the cloud infrastructure, so that as you, as a chip customer who wants to go build a certain custom chip, you don't have to worry about a lot of those things. The entire thing will be integrated into web application, and you'll be able to customize your chip to your needs. And a bunch of IPs, for example, would be onboarded onto the platform already, ready to go, integrated into the chip platform. So you, as a as an architect, would just need to go worry about some of the blocks that you are interested in customizing. All the other IPs that you need would be onboarded onto the platform. And SiFive would already have fab relations. So for example, we would be having relationships with the Samsung foundry, TSMC, Global Foundries, and other foundries. So you will be able to come and leverage all those relationships that were built already. So the whole idea is After manufacturing your custom design, we would package and test the parts, and we would ship working parts to you so that you don't need the entire operations at your team. So with this, I believe we can build a billion-dollar chip company with 13 people. And that, because you don't need to worry about all that. You can be focused on the part that matters to you, maybe in your garage. So with all this technology, we've already been making a lot of relationships with the ecosystem partners. And in order to build our technology and prove our technology out, we've been building some reference platform chips. So the first chip that we built is a 32-bit low-power microcontroller platform. So this is an actual chip that we taped out in TSMC 180 nanometer process technology node. There's the E3 series SiFive RISC-V core IP in it, and there's a bunch of peripheral IPs in it already integrated. So this chip has been put on a Arduino Compatible RISC-V development board with the chip on it. There's all the software that comes with it. So you can buy this board at $59. You can go play around with it. You can try to map your application onto it. There's probably something that doesn't quite work for you. Then you can just come to us, and you can customize your microcontroller for your application. We've also been working on our 28 nanometer Linux platform here. So at the heart of this platform, there is a quad-core application processor plus an embedded processor core complex. We've pre-integrated a DDR controller PHY. We've also onboarded a bunch of peripheral IPs on it with clock generation and all that. At the top, you can see there's a block called Chiplink. The internal buses of our platforms use an open standard called Tiling, which we've been developing. Chiplink is a serialized version of Tiling that goes out of the chip so that you can extend the SoC bus interconnect to the outside world. So in this particular situation, you have terminated the Chiplink with some FPGA so that you can go build your accelerators on the FPGA. So you can co-simulate or co-emulate, co-design your accelerator with an actual chip platform that has been taped out. So the idea here would be that once you start working on this platform, you would go buy this kit. You would start working on your accelerator on the FPGA. And once you're ready to go build a chip, you would come to us with the accelerator block, and we would take it from there. We would integrate all the same IPs. We would put down your accelerator block. We would run all the synthesis flows, the place and route flows on the cloud. We would take care of the fab relations. We would go package and test the chip, and we will ship working dies back to you at a very reasonable cost. As a matter of fact, we've been working with the ecosystem partners to enable the cloud infrastructure. We've recently taped this, this chip out on Microsoft Azure Cloud Platform using Cadence tools in the cloud. So we've actually been building up all these technologies and partnerships to realize this vision. So we put this chip on a development board as well. We call that board HighFive Unleashed. It has 8 gigabytes of DDR. It has gigabit Ethernet. And the FMC port that you see on the lower right down there is something that you can plug into an FPGA board. That's a Chiplink connection outside the chip. So this board is a little bit more expensive. It's $999, but nonetheless, a lot of people have been loving to use this board because this is the first and only Linux board out there with RISC-V on it. So there's a lot of software that we built that works with this chip. Not to mention all the assemblers, compilers, C libraries, all that have all been upstreamed. Operating system ports such as Zephyr, Linux, FreeBSD, as I mentioned, are all upstreamed. And the emulator ports like QEMU and things like that have been upstreamed. And really exciting news, RISC-V distribution ports are also in progress. Debian, Fedora, Open Embedded, OpenWRT, Gentoo all have RISC-V ports to it. And the really cool thing is it's not just SciFi working on this. It's the open source ecosystem working together. The favorite thing I like to say is other companies who have proprietary ISAs only have 300 software engineers working on it. We have a lot more people working on the RISC-V software ecosystem. Just to mention a couple companies here who have really been helping out. Andes is another core IP company. So it's kind of cool, you know, we have similar products, but yet we work together on the same software. And to prove my point, here's the Debian distro bring up status. You can kind of see that hockey stick and that's going up. This is the number of packages that are ported per architecture. You can kind of see that hockey stick. That's RISC-V. That, from 0 to 80%, it took us 3 months to go port that many number of packages. And interestingly, now RISC-V has more packages than IA64 on Debian. So I'm really proud of that. So a lot of people have been putting a lot of work into building the RISC-V software ecosystem together. The really cool thing about this is if there's something that you rely on but don't have, you can go work on it. And you can make the RISC-V software ecosystem better together. OK, so I briefly talked about the FPGA connection off the HighFive Unleashed board. So we've actually built an expansion board together with Microsemi. So you can see the HighFive Unleashed board on your right. The big board in the middle is the Microsemi FPGA expansion board. The one that's under the heatsink is the PCIe switch, which breaks out into a X1 PCIe connector and an X16 PCIe connector. And there's some other USB connections, SATA, and there's an M.2 on the back side. So with this board, you can actually plug in a graphics card in the X16. And on the X1 slot, you can put USB and other PCIe devices, and standard Linux software would just work out of the box. So with that, you can boot Debian on a monitor, and you can also bring up a web browser on RISC-V. This is Google Maps. That big black building there is SiFive. I thought it was kind of cool that the chip can kind of project where a lot of engineers have been working at. Maybe it's not as cool as I think. There's no reaction. I think it's cool. So there's a lot more software that runs. So standard USB webcams all work. There's TuxCart running in the back, while Twitter's and Tops all working. And you remember the accelerator that I talked about, NVDLA, the open source edge inference engine? So we mapped that onto the FPGA, and we drive it with RISC-V. And this is YOLO v3 running on the NVDLA accelerator using the webcam, all under RISC-V Linux, under the Debian port. So I think this picture kind of captures the current state of the RISC-V software and kind of the vision of the new world that I'm thinking about, where a lot of people, companies, open source IP, there's open source developers who want to build cool things, there's processors, there's a cheap $2,000 development kit that you can buy where you can map these accelerators. And once you've done all that, you can come to a website, use a web application, and then boom, you have your own custom chip at a very reasonable price. All available under some seed funding amount. That way, I think we can build a lot more custom chips. So if you're interested, please come visit our website. It's scifive.com to go build silicon at the speed of software. So start designing today. And if you want to learn more about RISC-V, please come to the summit in about a month. Thank you very much.
Just a quick question. Is there any addition of this cloud service for students in universities?
Yes. That was part of the vision, where once we have fully built out the chip designer, which is currently under construction, we wanted to open it up to universities undergraduate courses as well as graduate courses so that people can start building a lot of chips. And especially, when was the last time you met an undergraduate who was so passionate about hardware?
Actually, never, but go ahead.
I want to change that. I think without these young people being inspired to build hardware, to build these things, I think as a hardware industry, we're not going to do so well. You know, I always say the hardware industry is only $400 billion when the software industry is $1 billion. You know, but one thing that I always point out to my software friends is, guess what? Software runs on hardware. If you don't have hardware, there's no software. So I really want to change the perception of hardware being this kind of dark thing where you shouldn't go do. I really want to change that with this. And I think the way to change that is to show how simple it can be to go build chips to do cool things. And with this cloud service, I really believe that we can actually have more parts of the globe go build chips. So right now, you have to be in a pocket in somewhere around a couple cities in North America, a couple cities in China, a couple cities in Korea, a couple cities in India. And if you're not there, you can't really learn. You can't really build chips. I think the way to break out of that is having these web services and have donations from a lot of generous people to go fund university programs to have access to this product. Thank you. Thank you very much.
Thank you very much for the talk. I love the vision here. Can you compare and contrast a little bit the choice of Chiplink versus PCIe, and maybe why you didn't choose PCIe for your expansion?
That's a great question. PCIe, as of today, cannot really, by itself, carry coherent messages across, the main CPU and the accelerators. Chiplink, so Tielink is built to be a coherent interconnect, and Chiplink can ship coherent messages back and forth. So something outside can cache the main memory which is connected to the CPU die, and vice versa. So that's part of the reason. So we're not just trying to go develop all of our new standards. Tielink and Chiplink is one that was necessary. We're also looking into building C6 type things as well. Okay. So everything is under consideration right now. And the whole vision of this template idea is that I don't want to go judge what gets on the chip. If somebody else wants their own standard, they're more than welcome to go develop IP and publish a template which has that piece on it. And if other people buy into it, they can come and instantiate that template with that particular interface on it. So as a design platform kind of company, we'd like to go investigate all the different standards out there that is accessible. PCIe, C6, Chiplink, and all those things will be available on our platform.
Yeah. Thank you.
Thank you.
Hi. So usually that kind of infrastructure assumes a big base, lots of people using it and developing. What kind of expectation do you have? So is everybody out there going to design chips, or what's the market that
right.
you envision?
So I think the design platform that I'm talking about is useful for very big companies like Samsung, all the way down to small companies, which only 2 people are there to go build companies. I think starting from big companies like Samsung, there's a lot of internal IPs that I believe that you have, and it's probably very hard to have other parts of the company go use the IP. So I believe this template idea could be privatized as well for big companies, so that there are certain teams building IPs, there are certain teams building templates, and those private templates could be shared between other divisions of the company. I think the public version of this entire design platform would be, so at SciFive, we have open sourced two SoC platforms, the Freedom Everywhere and the Freedom Unleashed platforms, are, as a matter of fact, all open sourced. So you can go to our GitHub and you can go download the RTL code for the SoC. There are scripts to go map them to the FPGAs and all that. So for the public template idea, the customer base is really all the open source and companies and everyone who has access to internet. And that's really the idea. And I like to build services to go have people do development on their certain IP blocks. We would have services to help regressions and all that, so that it will be very easy to go develop hardware if you have a laptop and an internet connection.
Okay. I think it's my turn. Thanks very much for the speech. So I have 2 questions. One is, what's the estimated production cycle when people submit their RTL code to the website? And the second one is how to make sure the IP security, because there are more people involved at the backend, right? When the people just submit the readable code from the website. Thank you.
Those are great questions. So the plan is to build a service which can turn around chips within 1 or 2 months. Really, the fab cycle, typically 1 day per mask. So typical 28 nanometer would have somewhere between 45 to 60 masks. So the fab cycle itself would be, somewhere between 2 months and, slightly less than a month. So we would like to turn the entire product around in less than 3 months. So the entire infrastructure to go build chips is all automated, and we'd like to have less human involved in the entire process. Mm-hmm. So for example, our entire chip flow that we're building at SiFive, really, we don't have pre-silicon ECOs, because we built an infrastructure which can replicate the entire system, the entire process of building a chip from scratch to a DRC LVS clean GDS, right? So with that, I believe I can turn that down to something below 3 months. IP security is a great problem. I think, we have to solve it together. But I think the software folks in the cloud infrastructure side has already been solving those type of problems. We put a lot of health data and government data all in the cloud. So I think we would just basically piggyback on all the efforts that has been going on the cloud infrastructure side.